Imagine opening a picture of the deep sky and feeling your brain hesitate. The photo looks wrong. A single galaxy seems to appear in several places at once. In another frame, a perfect ring of light hangs in the dark like a halo. Elsewhere, a thin jet bursts from a galaxy's core and appears to outrun light itself. These scenes feel like magic tricks played on reality. They are not tricks. They are the universe revealing how space and time really work. This story begins with gravity, but not the everyday pull you feel when you drop a cup. Think of gravity as geometry. Mass does not only tug on things, it bends the fabric of space and time, and light follows those bends. When a massive cluster of galaxies sits between us and something even farther away, that cluster acts like a lens. It has no glass. It has gravity. It stretches, magnifies, and sometimes multiplies the distant source into arcs, rings, and mirrored copies. The most striking example is the Einstein ring. Picture a flashlight shining straight at you from behind a crystal marble. If the light, the marble, and your eye line up just right, the marble spreads the beam into a bright circle. In space, the distant galaxy is the flashlight, the intervening mass is the marble, and Hubble is the eye. Perfect alignment turns the background galaxy into a ring around the lensing mass. A small misalignment creates partial rings and graceful arcs. You are not seeing a portal or a doorway. You are seeing light bent into a circle by gravity. Lensing can get even stranger. A single background galaxy can be copied into several lopsided images arranged like beads. Each copy took a different route around the lens, and each route took a different amount of time. Lensing is not only a magnifying glass, it is also a clock. A flare that happens once at the source can appear and then reappear later as the delayed light from each path reaches us in turn. Astronomers read those delays the way a doctor reads a pulse. The timing tells us how much mass the lens holds and how that mass is spread out, including dark matter that does not glow. Now, about that jet that looks faster than light. Are we watching a crack in physics? Number. We are watching perspective, compressed time and distance, in a way our eyes are not built to handle. The jet is a beam of particles launched from near a supermassive black hole at a speed very close to light. If the jet points almost toward us, the light it gives off along the way has less and less distance to travel with each new burst. The later parts of the jet are physically farther out, but because they aim along our line of sight, the travel time shrinks from frame to frame. Draw a line through those positions and divide by the tiny time gaps, and you will compute an impossible speed. Relativity is not broken. The illusion is. To feel this without equations, imagine a fast plane flying almost straight at you while dropping flares every second. Each new flare appears almost on top of the previous one and reaches you with less delay than you expect. If you measured the spacing and the arrival times without considering the angle, you would calculate a ridiculous speed. That is the same trap our brains fall into with so-called superluminal jets. Astronomers correct it by measuring three things: the angle of the jet, the apparent speed across the sky, and the redshift of the host galaxy. From those numbers, they recover the true speed, which is high, but still under the cosmic limit set by light. The beauty of Hubble's impossible images is that they make abstract physics feel close. You can sense the stretch in blue arcs curling around a golden cluster. You can sense the symmetry in a ring that should not exist in empty space. You can feel the jolt of a jet that seems too fast to be real. Underneath each scene is the same idea. Space is not a rigid stage. It is flexible. It bends around mass. It changes the routes that light can take. It can delay a signal without touching the source. It can turn a tiny spark into something we can finally see. This matters. Gravitational lensing lets us weigh things we cannot see. It reveals the skeleton of dark matter in clusters. It turns the universe itself into a telescope, letting Hubble and other observatories study infant galaxies from the first billion years after the Big Bang. Time delays in lensed flares and supernovae help us measure how fast the universe expands. Even the not really faster than light jets are gifts. They teach us about the engines at galactic centers, where magnetic fields and gravity braid together to launch matter into space. So the next time you see a ring of light, a doubled galaxy, or a racing jet in a Hubble image, remember this: the camera is not lying. Your intuition is catching up. The universe is inviting you to upgrade the way you think. In the chapters ahead, we will take the illusion apart, piece by piece. We will learn how mass warps space-time and why light obeys those curves. We will decode Einstein rings, arcs, and crosses. We will watch a lensed supernova blink in delayed echoes and see how that blinking turns into a ruler for cosmic distances. For now, hold one picture in your mind: a ring of light floating in darkness. It is not a trick. It is a straight story told along a curved path. That is the heart of the illusion, and it is more beautiful and more honest than any stage magic could ever be. Before we pull apart Hubble's impossible pictures, we need a simple map. 3 actors make the show: a distant source that emits light, a massive lens in the middle, often a galaxy or an entire cluster, and us, the observers. When they line up, the lens's gravity bends space-time so that more than one straightest path exists from source to eye. Hubble, staring from Earth orbit, records those paths as arcs, mirrored twins, or a glowing ring. Nothing supernatural, just geometry made visible. 2 quick comparisons help. A glass lens bends light because the material slows the wave. Gravity bends light because mass curves the stage the wave travels through. And like a mountain that forces drivers onto different roads around it, mass forces light onto different routes with different travel times. Space-time is the landscape, mass is the mountain, photons are the cars. Different routes, different delays, same destination. Your telescope. Astronomers sort lensing into 3 flavors. Strong lensing is the dramatic one. Big arcs, crosses, and near-perfect rings called Einstein rings, produced by tight alignment with a massive lens. Weak lensing is subtle. A crowd of background galaxies looks slightly stretched in the same preferred directions. By measuring those tiny shape biases across an image, scientists draw a map of the invisible mass dark matter binding a cluster. Microlensing is quieter still. A single star can brighten for days or weeks when a compact object passes in front of it. And in our own galaxy, the same trick has revealed otherwise hidden exoplanets. Hubble is a master of the first 2 flavors. In deep programs like Frontier Fields and Relics, teams combined strong and weak lensing. The giant foreground clusters acted like cosmic zoom lenses, magnifying baby galaxies from the early universe, while the gentle, statistical stretch revealed where the cluster's dark matter actually sits. NASA and ESA releases from those campaigns show the famous blue arcs curling around golden cluster cores. The color contrast is not just pretty, it helps separate cooler foreground light from bluer, star-forming background galaxies. Why do rings and arcs appear at special radii? Because there's a critical circle around the lens where magnification soars. Inside that circle, tiny alignment shifts cause big changes in the number and shape of images. Astronomers call the circle the Einstein radius. Its size depends on 3 things: the lens mass, the distances to lens and source, and the overall geometry of the universe. Measure that radius carefully in Hubble data, and you can weigh the lens. No need to see or count every star. Time, not just shape, is part of the story. Each lensed image is a snapshot of the source taken at a slightly different moment, because each light path has a different length and passes through a different gravitational potential. If the source flickers, flares, or explodes, those changes ripple through the multiple images out of sync. Catching those echoes lets astronomers measure the mass profile of the lens and the scale of cosmic expansion. The method is called time delay cosmography. It turns a lensed flare, or supernova, into a natural stopwatch. A caution about illusions. Lensing can tempt viewers to think we're seeing portals or violations of physics. Symmetry feels like design, and duplication feels like science fiction. But the lens equation is blunt. Where mass sits, how light bends, and when that light arrives are all consequences of general relativity. The theory predicted the effect long before Hubble photographed it. One early proof arrived in 1919, when starlight grazing the sun was measurably deflected during a solar eclipse. Modern space telescopes repeat that test with exquisite precision. Don't mix lensing with mirages. On a hot highway, layers of air at different temperatures bend light and make puddles that aren't there. That's refraction in a medium. Gravitational lensing needs no medium. Space itself is curved, and light follows the curves. That's why lensing works in the vacuum between galaxies and why it lets us see objects so distant that even Hubble would otherwise miss them. For a clean example, picture the Einstein cross. One quasar split into 4 points wrapped around a foreground galaxy. You aren't seeing 4 quasars. You're seeing one quasar, 4 ways, each path bent by the lens's mass, and each arrival delayed by minutes to days. Track the brightness of each point, and you can read off the delays. Fit those delays with a lens model, and you recover the mass distribution. Compare that to what the galaxy's stars alone would weigh, and the missing mass points to dark matter. Hubble has also revealed rings so precise they look computer-generated. In those cases, the alignment is so tight that the background galaxy's image wraps almost all the way around. Zoom in, and the ring isn't perfectly uniform. It has bright knots and dim gaps. Those bumps are clues. They tell you about clumps in the lens satellite galaxies, subhalos of dark matter, or small departures from a smooth mass map. In other words, tiny wrinkles in the ring sketch tiny wrinkles in the lens. Carry this mental model forward. Light wants to go straight, but straight means geodesics, the straightest lines in a curved space. Mass curved space. Curved space can offer multiple straightest lines between the same 2 points. Hubble collects the light that took different lines and hands us copies, arcs, and circles. From their shapes and delays, we weigh the lens, map its hidden skeleton, and see farther back in time than our hardware alone would allow. In the next section, we'll slow an Einstein ring into steps, source, lens, observer, and show exactly how a circle appears, where the bright spots come from, and how a tiny misalignment turns perfection into graceful arcs. Let's slow the ring down and watch it form. Picture 3 actors lined up in space. A distant galaxy glowing with starlight, a massive lensing galaxy or cluster in the middle, and us with a telescope far away. Light leaves the background galaxy in all directions. A special set grazes the foreground mass, rides the curves of warped space-time, and then swings back toward our line of sight. Hubble collects those rays, and on its detector, a circle appears. Why a circle instead of a smear? Because the lens is nearly symmetric. If the source sits directly behind the lens center, every direction around that center bends light by the same amount. The result is a ring at a specific radius, the Einstein radius, where the lenses pull and the geometry of the distances balance. Move the source closer or farther, and the ring grows or shrinks. Change the lens mass, and the ring tightens or loosens. In practice, the ring is a built-in ruler written in light. Real lenses are never perfect. Mass in the universe is lumpy. Stars, gas, dark matter clumps, and companion galaxies all tug on passing rays. Break the symmetry a little, and the perfect circle relaxes into bright arcs. The brightest parts mark where the lens is focusing light most strongly, like the rippled highlights at the bottom of a swimming pool on a sunny day. Physicists call those focus zones caustics. When a background galaxy approaches a caustic, its image can split, stretch, and brighten dramatically. A kitchen table version of the effect is easy to imagine. Shine a flashlight through a wine glass onto a wall. As you slide the glass, the pattern on the wall blooms into curves with sharp, glowing edges that dance and merge. In the sky, The lens plays the role of the glass, the distant galaxy is the flashlight, and the celestial sphere is the wall. Cross the caustic, and the number of images changes by 2. That is why strong lenses show 2, 4, or more copies of a single distant object. There is often a 5th image hiding in plain view. In a smooth lens, general relativity predicts an odd number of images. The extra one forms very close to the center of the lensing galaxy and is highly demagnified. It is usually drowned by the galaxy's own glow and dust. With careful modeling and very deep observations, astronomers have teased out this faint central image in a handful of systems. Not all arcs look alike. If the lens's mass is stretched like a rugby ball, the ring becomes a pair of long banana-shaped arcs. If the mass is more boxy, arcs can kink into bright knots at special angles, called cusps. Place the source near a cusp, and 4 bright points pop out around the lens, the famous cross pattern seen in some quasars. Each point is the same quasar viewed along a different path, and one image is mirror-flipped relative to another. Color and texture across a ring are clues too. Star-forming patches in the source show up as repeating blue knots along the arc. A spiral arm can be copied and stretched into several segments. By matching those repeated features, scientists tie the multiple images back to the same places in the source galaxy, like solving a jigsaw puzzle whose pieces have been bent and enlarged. The better the match, the tighter the map of the lens mass must be. Time layers on top of shape. Each image arrives with its own delay because each path is a different length and passes through deeper or shallower gravitational wells. If the source flickers, the flicker ripples through the images at different times. Measure those delays and you recover both the geometry of the lens and a handle on the cosmic expansion rate. Use a lensed supernova and you get sharp, one-time pulses. Use a lensed quasar and you get a noisy, ongoing light curve. Either way, the universe itself provides the stopwatch. A few terms help, even without equations. The critical curve lives in the image we see. It wraps around the lens where magnification soars. Map that curve back to the source plane, and you get the caustic, the boundary across which the number of images changes. When the source touches or crosses the caustic, we get long, bright arcs, and sometimes near rings. When the source sits comfortably away from it, we see fewer, rounder images with lower magnification. Hubble's sharp vision makes these structures visible. Its advanced camera for surveys and wide-field camera 3 can separate knots only a few hundred parsecs across in distant galaxies once the lens stretches them. That is one reason lensed fields are so powerful. They turn a barely detectable smudge into a readable photograph. Lensing is honest about its limits. It magnifies and it distorts, and if we want the true picture, we must invert the effect. Astronomers build lens models that include the main mass, the overall shape, and small substructures. When a prediction fails, the fix may be a hidden clump of dark matter or a small change in the lens's slope. Bit by bit, the model sharpens until every arc, knot, and delay is accounted for. Hold this summary. A perfect alignment gives a ring. A near miss gives arcs and multiples. Caustics mark where images split and magnification booms. A faint central image whispers about the core. Colors repeat along arcs because the same star-forming regions are echoed by the lens. Delays turn geometry into timing, letting us weigh the lens and measure the growth of space itself. The scene feels strange only until you know the rules, and now you do. Apparent faster-than-light jets sound like science fiction, but the effect is a straightforward play of geometry, timing, and very high speed. Start with the engine at the heart of a massive galaxy, a black hole millions or billions of times. The sun's mass feeds on gas and dust. In-falling material flattens into a hot, bright disk. Magnetic fields anchored in that disk wind up like coiled springs and fling some of the matter away from the core in narrow beams. Those beams' jets blast out in opposite directions at nearly the speed of light. Now picture one jet aimed almost toward us, not perfectly, just a little off our line of sight. The jet spits out bright knots of plasma like beads on a string, each knot shining as it travels. Here is the trick. Later knots have less distance for their light to cover before reaching us. A knot created farther down the jet is physically more distant from the black hole, but because the jet points almost at us, its light takes a shorter path to our telescope. Compare where the knots appear on the sky with when their light arrives, and the implied speed can look superluminal. Make a mental movie. A race car drives almost straight toward your camera and fires a flare every second. Each new flare has less road left to cross. The first launches far away, and its light takes longer to reach you. The second launches closer and arrives sooner than you expect. Divide the apparent spacing by the tiny arrival time gap, and you get a ridiculous speed. That is superluminal motion, not a broken law, just a trick of angles and timing. Relativity adds two more pieces that explain what Hubble and radio arrays actually see. First, relativistic beaming points. Radiation forward, the approaching jet is boosted and looks brighter and faster. The receding jet is dimmed and often disappears. This is why so many galaxies show a one-sided jet. We are not missing the other side because it failed to form. We miss it because special relativity points the light away from us and stretches its clock. Second, the color and brightness of the knots tell us how close they are to light speed. As the jet barrels ahead, its radiation is Doppler shifted. Strong beaming nudges the spectrum and sharpens features. Combine those shifts with knot positions measured over years, and you can recover both the true speed and the angle the jet makes with our line of sight. In practice, astronomers track the same knots across many images, fit their apparent motion, and solve for the geometry. The result is always the same: extreme but sublight speeds and small viewing angles. You might ask whether anything in the universe really moves faster than light. The simple answer is no for objects moving through space, but yes for patterns that carry no usable signal. A shadow can sweep across a wall faster than light if the spotlight and wall are far apart. The bright edge of a light echo the place where dust lights up after a flash can expand faster than light across a cloud. Those are moving fronts, not couriers. They do not transmit information or energy faster than nature's limit. Jets offer a useful mirror for Hubble's impossible lensing pictures. Our eyes want to trust size and symmetry. A long, straight feature that seems to jump across the screen reads as fast. A ring that hangs in darkness reads as artificial. But the universe is patient and loves perspective. In lensing, mass curves the paths that light takes to us, creating copies, arcs, and rings. In jets, motion bends our sense of time, making speeds look unreal. In both cases, the cure is to think in space-time, not in flat, everyday space. A nearby example helps. The giant elliptical galaxy, MADI 7, hosts a jet that stretches for thousands of light-years. Decades of observations with space and ground telescopes show bright knots sliding along that beam. Some seem to outpace light when you plot their apparent speeds on the sky. Measure carefully, and the illusion dissolves. The jet points fairly close to our line of sight. The knots move just under light speed, and any calculation that ignores the angle overestimates the true motion. What about cases where different parts of a jet brighten almost at once, as if a signal jumped ahead instantly? Often that is a shockwave plowing through the beam, like a pressure front in air. A shock can light up many regions nearly together without any physical chunk of matter teleporting. The pattern moves, but the particles themselves remain subluminal. It is the same logic that lets the bright spot of a laser pointer race across the moon faster than light without any red dot particles skimming the surface. The payoff is practical. Jets are laboratories for extreme physics. Close to the black hole, they show how magnetic fields extract energy from a spinning spacetime. Farther out, they sculpt a galaxy's gas, heating halos and slowing or triggering star formation. When a jet points our way, its boosted light lets us study the heart of a galaxy far beyond the reach of ordinary telescopes. When it points away, we learn about the environment that dims it. Either way, the lesson is consistent. Light speed is the limit. Perspective can fool us, but physics holds. Hold that idea as we return to Hubble's deep fields and their graceful arcs. One set of illusions comes from gravity acting on light paths. The other comes from motion acting on our sense of time. Both can be untangled with careful measurements. Next, we will unravel how astronomers turn warped shapes into maps of invisible mass, and why those maps changed what we believe about the universe's contents. When you look at a Hubble frame full of blue arcs curling around a golden cluster, you are seeing a ghost made visible the gravity of matter that does not shine. Turning that ghost into a map is the next step. Astronomers begin with what Hubble measures: the positions and shapes of distorted background galaxies. From those observables, they work backward to the mass distribution that bent the light. The equations come from general relativity, but the idea is simple. Light took several straightest routes through a warped landscape, and our job is to rebuild the landscape from the paths it forced light to take. There are two main toolkits. The first is strong lensing, long arcs, crosses, and near-perfect rings. Because the distortions are large, the relative positions and orientations of the images carry a lot of information. Modelers start with a reasonable guess, like an oval halo for the main lens plus a few satellites. They ray trace light from a trial source and compare the predicted arcs to the real ones. If they do not line up, the model is tweaked and tried again until every arc, knot, and mirror flip is reproduced. The second toolkit is weak lensing. Most background galaxies are not turned into arcs. They are nudged a little. A single galaxy's shape tells you almost nothing because galaxies have their own ellipticities, but a crowd is honest. Average the orientations of thousands of faint smudges and a pattern appears. A gentle, tangential stretch that encircles the mass. Plot those preferred directions and you get a field of tiny arrows that outline the hidden skeleton of the lens. That cosmic shear field is inverted into a wide-angle, low-resolution mass map that complements the detailed strong lensing core. Neither method is perfect alone. Strong lensing weighs the dense center. Weak lensing sketches the outskirts. Combine them, and the picture locks together from center to edge. Add one more ingredient: stellar motions inside the lensing galaxy, or the glow of hot gas in X-rays, and the map tightens again. Each tracer carries its own bias. Together, they cross-check one another and leave less room for wishful thinking. What drops out is both a number and a picture. The number is the mass inside the Einstein radius, the weight required to put the arcs where they are. The picture is a contour map of surface mass density. It shows smooth hills where mass piles up and smaller bumps where substructures hide. Those bumps matter. A smooth model often fails to match the exact brightness of multiple images. The fix is usually to add clumps. Satellite galaxies you can see, and darker subhalos you cannot. By measuring how big a tweak each image needs, astronomers infer how massive those hidden clumps must be. Sometimes the maps reveal a twist that changed astronomy's storyline. In collisions of galaxy clusters, the hot gas, the bulk of luminous matter, slows and lags behind. Lit in X-rays where it is shocked. The lensing mass, however, marches on with the galaxies. Light says one thing, gravity says another. That separation is hard to fake with tweaks to gravity alone, but natural if most of the mass is in a weakly interacting, invisible form. Lensing, paired with X-ray views, turn those scenes into clear cases for dark matter. Even within single clusters, the weight does not follow the light. Stars make up only a small slice of the total. The lensing map is more extended than the starlight. Weak lensing panoramas show that halos are not neat spheres. They are stretched, twisted, and full of substructure. The same messy architecture predicted by simulations of cold dark matter. That agreement shapes here, shapes there, built confidence that the invisible component is real and behaves as a cold sea of particles. Lensing has blind spots called degeneracies, places where different mass layouts can mimic each other. 1. The mass sheet degeneracy lets you smear a little uniform mass over the whole field without changing shapes much. Another trades a steeper central cusp for more mass in the outskirts while keeping arc locations similar. Astronomers break these ties by adding independent information. Stellar velocities in the lensing galaxy, time delays between multiple images of a variable source, or the magnification of objects with known sizes and brightnesses. This may sound like educated guesswork, but it is disciplined and testable. Teams fit both parametric models with a handful of physical components and pixel-based, free-form maps that let mass vary across a grid. They run blind challenges on simulated skies to check whether their codes recover the planted truth. They publish multiple models for the same cluster, so other groups can compare predictions. When independent paths converge on the same total mass, the same substructures, the same time delays, confidence rises. The payoff is not just a census of mass. Strong lensing magnifies like a zoom lens, so distant dwarf galaxies that would usually hide leap into view. Hubble has used that gift to study star formation in the universe's first billion years, resolving compact star-forming clumps smaller than it could without the lens. Weak lensing, spread across many fields, underpins measurements of how cosmic structure has grown over time. Together with other probes, those measurements point to an expanding cosmos whose rate changes. In short, lensing is both microscope and yardstick. Underneath all that detail is a plain message you can carry without equations. Arcs, rings, and stretches are not pretty accidents. They are measurements. Hubble's impossible pictures let us weigh what does not shine, find clumps we cannot see, and test our ideas about matter and gravity. So far, the verdict is striking. Most of the mass in the universe is invisible to our eyes and to Hubble's mirror, but not to gravity. Lensing lets us sketch its outline, and the outline matches the story told by other messengers, stars, gas, and the afterglow of the Big Bang. Next, we will watch a lensed supernova blink along multiple paths and use those echoes to turn geometry into a clock and then into a ruler for the expanding cosmos. Imagine a distant star that explodes only once, yet our telescope catches it more than once. First, a small patch near a galaxy cluster brightens and fades. Weeks or months later, another patch in the same field repeats the same rise and fall. Then, a third echo appears. We are not watching a star that refuses to die. We are watching the same light curve arrive along different routes through curved spacetime. A lensed supernova turns gravity into a delay line and the universe into a clock. Here is the rhythm. A massive lens sits between us and the supernova. Rays that dive deepest into the lens's gravitational well take the longest, like a hiker who descends into a valley and climbs out again. Rays that swing around the outskirts arrive sooner. Each image on Hubble's detector is the same event, stamped with a different time. Record the brightness for each image over days and weeks. The offsets between their peaks are the time delays. Combine those delays with a tested lens model, and you can convert geometry into distance, a time-delayed distance that encodes the expansion rate. The leap from idea to proof came when astronomers found a supernova split into several images behind a rich cluster and predicted in advance when and where another image would appear. They watched, the date arrived, and the sky delivered. The reappearance was a cosmic rerun, right on schedule. That success validated the mass model of the cluster and showed that gravity's delays can be used like a stopwatch. Quasars were the original training ground. A quasar is a bright, restless source powered by a feeding black hole. When lensed into 2 or 4 images, its natural ups and downs play on a split screen. Observers track the brightness in each image for months or years. Cross-correlating the light curves yields precise delays. Those delays, plus a careful map of the lens and the mass along the line of sight, turn into a measurement of how fast the universe expands. The method's strength is that it depends on timing and geometry rather than a local distance ladder. There are snags to handle. Small masses sprinkled through the lens and along the line of sight add or subtract tiny amounts of delay. Dust can redden one image more than another. Stars in the lensing galaxy can microlens a quasar's accretion disk, making one image briefly brighter or dimmer and masking part of the true variability. With supernovae, the light curve shape helps. We know roughly how a type Ia or a core collapse event should rise and fade, so we can match the echoes even when microlensing paints extra bumps on the light curve. Turning delays into a Hubble constant also requires a flexible, realistic model of the lens. The delays scale with a combination of distances that depends on the expansion rate, but those distances are filtered through the mass map. If the center is too steep or too shallow, the inferred rate will shift. That is why time delay studies pair sharp, space-based imaging with spectra that measure the motion of stars in the lensing galaxy, and with deep counts of galaxies in the surrounding field. The more angles and data sets we add, the tighter the answer becomes. Why bother when there are other ways to gauge expansion? Because agreement and disagreement both teach us. If time delays match values inferred from the afterglow of the Big Bang, our picture looks self-consistent from early times to now. If they differ from measurements based on nearby supernovae and galaxies, the tension might hint at overlooked systematics or new physics. Lensed supernovae are especially helpful here. Their one-time, clean pulses and relatively uniform behavior make it easier to identify microlensing and dust. Time-delayed echoes also carry local surprises. In a smooth model, the brightness ratios of multiple images should follow from the geometry. When they do not, the culprit is often small-scale structured dwarf satellites and dark matter subhalos hiding in the lens. A mismatch of only a few tenths of a magnitude can signal a clump with a mass of millions of suns, far below what we could weigh any other way at such distances. In this way, a single dying star can reveal the pebble-textured surface of an otherwise invisible halo. There is even a practical gain for studying the supernova itself. In a lucky geometry, the first image arrives faintly, far from critical curves, and serves as an early warning. The later, more magnified images arrive after a predictable delay and can be caught at high signal-to-noise. That lets astronomers schedule precious telescope time to take spectra at the exact moments when the physics inside the blast is most revealing. The cosmos, via lensing, becomes its own alert system. Hubble's role is to spot these rare alignments and measure them with stable, sharp vision. It resolves images separated by less than an arcsecond and provides steady light curves. Ground-based surveys sweep wide areas to find the transients. Space-based imaging disentangles the crowding and nails the timing. New facilities will extend the story, harvesting many more lensed supernovae and following them in detail, pairing infrared colors with high-contrast imaging to measure delays and magnifications with high precision. The headline is simple. The universe makes copies and staggers their delivery. We read the stagger to learn how the stage is built and how fast it is stretching. A single picture that looks impossible becomes a stopwatch and a ruler. It is a quiet kind of magic that rewards patience and a steady gaze, and it turns the deep sky into a laboratory for both gravity and time. Next, we will zoom back into the arcs and rings and look for the brightness glitches that betray hidden clumps of dark matter, why some rings have sparkles in the wrong places, and how those sparkles test what dark matter is made of. Sometimes a ring looks too tidy until you zoom in. Then you notice bright knots that do not match, or one segment that shines harder than any smooth model would allow. Those sparkles and mismatched patches are not mistakes in the picture. They are the fingerprints of hidden mass, small clumps that tug on passing light just enough to change the brightness without moving the images very far. In other words, the arc is telling you there is structure in the dark. Start with what a smooth lens would do. Imagine a foreground halo shaped like a soft oval, plus the light from its stars and gas. Feed that into a standard lens model, and it will reproduce the big shapes, where the arc sits, how far it stretches, where its mirror twins should appear. It will also predict how bright each copy should be relative to the others. Now compare those predictions with the Hubble image. If one piece is brighter or dimmer than expected, and the positions are still right on target, something extra must be bending the light locally. That something is a subhalo, a small mass clump made mostly of dark matter. There are two scales of mischief. The first is microlensing by individual stars in the lensing galaxy. Stars act like tiny lenses that can briefly boost or dim a point-like source, such as a quasar's compact core. Microlensing is fickle and time variable. It can change over weeks to months as stars move. The second is millilensing by subhalos weighing millions to billions of suns. Those clumps are big enough to imprint steady, spatial wiggles on an extended arc or ring. Catch a persistent brightness anomaly that does not flicker with time, especially in light from a larger region, and you are likely seeing a dark subhalo. Observers have tricks to separate the two. If the lensed source is a quasar, its broad line region is compact and vulnerable to microlensing, but its narrow line region is much larger and mostly immune. Measure flux ratios using light from the larger region, and any mismatch is more likely due to a dark clump than to stars. Radio and far infrared emissions are also extended and less affected by microlensing. When radio images of a lensed quasar show the wrong brightness pattern, the culprit is almost certainly a subhalo, not a twinkling field of stars. Extended arcs make the case even stronger. A ring is not just a set of points. It is a continuous curve of information. Small, localized kinks and brightenings along that curve betray where extra mass sits. Modelers can peel back the distortion by fitting a smooth lens and then mapping the residual wiggles. The technique is sometimes called gravitational imaging. Each wiggle corresponds to a small overdensity, often a dark satellite, too faint to see in starlight. Stack evidence from many systems, and you start to count how many subhalos exist at different masses. That count is a deep test of what dark matter is made of. In the cold dark matter picture, structure forms bottom up. Tiny halos collapse first, then merge into bigger ones, leaving a fossil record of many small clumps orbiting inside larger halos. Warm dark matter would erase some of those smallest clumps because its particles would have moved too fast in the early universe to settle into tiny wells. Self-interacting dark matter could smooth the inner density and change how subhalos survive. Lensing turns these abstract ideas into a census. If arcs and rings demand lots of small clumps, that supports the cold picture. If small clumps are rare, warmer or more collisional options gain ground. Line of sight structure adds another layer. A clump does not have to live inside the main lens to perturb the image. A small halo anywhere between us and the source can add a subtle nudge. Careful modeling includes that possibility. The practical effect is that subhalo counts from lensing are a mix of satellites bound to the lens and free-floating halos along the path. That sounds messy, but the two contributions can be estimated statistically, and both are valuable clues about how structure is distributed in the universe. Some anomalies are delightfully specific. A bright knot in the ring might line up with a dwarf satellite you can barely see. Add that dwarf to the model, and the arc's brightness falls back into place. In other cases, there is no visible companion, yet the data still demand extra mass. The fix is a dark subhalo with no stars. These invisible companions are exactly what cold dark matter forecasts in large numbers. Finding them with lensing is like dusting for prints at a scene where the suspect never turned on a light. You can think of a ring as a truth detector. A smooth model that fits the big picture must also survive the small tests. Does it get the knot brightnesses right? The slight twists correct? The tiny offsets consistent across filters and epochs? If it fails, it is not because gravity changed its mind. It is because the mass map is missing bumps. Iteratively adding substructure until the arc behaves teaches you, clump by clump, what the dark halo really looks like under a microscope. The payoffs reach beyond particle physics. Subhalos shape how gas accretes and how satellite galaxies live or die inside clusters. A clumpy halo sprinkles tidal forces across the cluster, heating gas here, stripping stars there, and sometimes triggering star formation in compressed pockets. Even the growth of central black holes can feel this textured environment. As infalling streams are jostled and stirred on their way in, the shiny picture of a ring becomes a report card on the ecosystem of a galaxy cluster. Precision matters, and that is why pairing Hubble's images with other wavelengths is so powerful. High-resolution radio maps can trace extended jets and star-forming regions through a lens, highlighting where brightness really deviates from smooth. Submillimeter and far-infrared views pick out dusty starbursts whose size protects them from microlensing, making them clean probes of subhalos. Spectroscopy adds velocity fields across the arc, turning brightness kinks into dynamical constraints. Each layer tightens the case that the anomalies are gravitational, not instrumental or atmospheric. The human-level summary is simple. When a ring or arc sparkles in the wrong place, the universe is whispering that there is more gravity there than the starlight admits. Those whispers, gathered across many systems, become a shout. Dark matter is not only out there, it is clumpy on small scales. That conclusion does not depend on one method or one telescope. It emerges when images, light curves, and spectra all point to the same stubborn bumps. Hold that thought as we step from the structure of the lens to the gift it gives us. A lens is not only a probe of dark matter, it is also a telescope we did not pay for. In the next section, we will use that free magnification to peer into the infant universe, how arcs and rings, paired with modern infrared eyes, reveal star-forming clumps, rotation, and chemistry in galaxies so young and small they would otherwise be invisible. Think of a massive galaxy cluster as a free telescope someone left out in space. It has no mirrors you can polish and no knobs you can turn, yet it magnifies distant objects all the same. When Hubble looks through such a cluster, the background universe is stretched and brightened. Tiny, early galaxies that would be too faint and too small to study suddenly bloom into readable shapes. Add modern infrared eyes that see the reddened glow from the universe's first billion years, and the lens becomes a cosmic microscope. Magnification is more than bigger. It changes what details we can resolve. A knot of star formation, only a few hundred light-years across, can be pulled wide enough for us to separate its bright core from its softer halo, and to trace how gas and dust wrap around it. Yes, the image is distorted, but distortion is a gift when you know how to undo it. Astronomers fit a lens model, map each stretched pixel back to its home in the source, and reconstruct the galaxy with far more detail than any unaided telescope could deliver. What do we find when we peel back the lens? Young galaxies are clumpy, turbulent builders. Instead of smooth disks, we see chains of bright star-forming knots stitched along faint backbones of gas. Some clumps rival the largest star-forming regions in today's galaxies. Others are larger still, giant nurseries pouring out newborn stars at breakneck rates. In a single magnified arc, we can pick out multiple cities of star birth and measure how violently they stir their surroundings. We can also watch these infant systems spin or fail to. With spectrographs that slice light by wavelength across the arc, astronomers read the motion of gas. A steady tilt in the wavelengths across the image signals rotation. One side of the galaxy is moving toward us, the other away. A messy, broken pattern signals a merger or a disturbed flow. Lensing turns faint smudges into kinematic maps, letting us tell a growing disk from a cosmic pileup long before either would be visible without help. Chemistry comes into reach. Starlight carries fingerprints of the elements mixed into a galaxy's gas. By sampling those fingerprints in different parts of a lensed arc, we trace how metals, astronomy's word for elements heavier than helium, are sprinkled across a young galaxy. Many show patchy, uneven enrichment, fresh, nearly pristine gas streaming in along cosmic filaments, mixing with pockets already seasoned by earlier bursts of stars. That patchwork teaches us how fast galaxies recycle material and how quickly they build complexity. This is where infrared sensitivity matters. The universe is expanding, and light from early times is stretched into redder colors by the time it reaches us. Instruments tuned to those colors can see features that mark star birth and warm dust in galaxies only a few 100 million years old. Through a lens, those baby systems jump above the noise. In some, we even spot compact star clusters so dense they may be the ancestors of today's globulars. Lenses also help us count what we would otherwise miss. The tiniest, dimmest galaxies are the building blocks of everything bigger, yet they are the hardest to tally. Strong lensing boosts them over our detection threshold. By measuring how many appear at each brightness behind many clusters, astronomers estimate how much faint light is hidden beyond our direct reach and how fast stars were forming when the universe was still young. Those counts help map reionization, the era when early light cleared the fog of hydrogen. Dust and cold gas, the raw fuel for stars, come into focus when we look with radio and submillimeter telescopes. Their maps, seen through a lens, trace heavy, dusty starbursts with enough detail to separate distinct pockets of activity. Pair those views with the cleaner, bluer starlight in Hubble-style images, and you see where new stars hide and how their energy leaks out. In some arcs, radio images track jets or winds that punch through the gas, carving channels that shape the next round of star formation. There is a price for the gift. Lensing does not simply magnify, it selects. We see the parts of the sky behind a lens, and within those, the places where magnification is highest. That bias must be measured and corrected when we turn counts and sizes into universal statements. By modeling the lens thoroughly, we compute the stretch for each piece of sky and recover how bright and how big a source would look without help. With that correction, the cosmic microscope becomes a fair ruler. Even the distortions are useful. A stretched galaxy gives us a longer ruler along one direction, and that can be enough to separate features we would otherwise blur together. Star-forming ridges split apart. The very act of being pulled into an arc makes hidden structure legible, the way a projector pulls a tiny slide onto a big screen. Why does this matter for the big picture? Because galaxy formation is about the messy, small-scale physics of gas, stars, and feedback, not just grand, smooth halos. Lensed views let us watch those processes at the scales where they actually act. We watch young clusters punch bubbles in their gas and see where inflows feed the center while winds choke them off. We map how metals spread. No simulation is complete unless it can produce the same clumpy tapestries that the sky, with help from gravity's optics, lays in front of us. So when you hear that a Hubble image made the impossible possible, this is what it means. A natural lens let a human-made telescope read the tiny handwriting of the early universe. Magnification did not only give us a prettier picture, it turned unreachable objects into laboratories. It let us time rotation, test chemistry, weigh dust, and watch the first organized pieces of galaxies take shape. In the next section, we will jump across the spectrum from radio to X-ray to see how the same lens gives different answers at different colors, and how combining those answers builds a fuller portrait of gravity's handiwork. Gravity is colorblind, but light is not. The same lens bends every wavelength by the same geometry, while each band highlights a different layer of the scene. Stitch those layers together: radio, millimeter, infrared, optical, ultraviolet, X-ray, and a simple arc becomes a full portrait. The trick is to remember what each color is telling you and how lensing subtly reshapes that message. Start with the coldest light. In the radio and millimeter, we see dust and molecular gas, the raw fuel for stars. Through a strong lens, dim, distant starbursts blossom into bright, resolvable swirls. Interferometers trace carbon monoxide lines that outline rotating gas disks, measure inflow and outflow speeds, and even pick out giant clumps where stars are forming. Because these emissions come from extended regions, they are largely immune to microlensing by individual stars in the foreground, which makes them clean probes of the mass rather than fragile, flickering points. Slide up to the infrared. Here, redshifted starlight from young galaxies emerges, mixed with warm dust. A lens can stretch those compact knots until crowded neighborhoods separate. A newborn cluster, a wind-blown bubble, a dusty lane feeding the core. Infrared spectra add chemistry, oxygen, nitrogen, and hydrogen lines that flag how enriched the gas is and how hard the local radiation field bites. Differential magnification matters. If one piece of the source falls near a caustic, it can be boosted disproportionately and dominate that band. So astronomers reconstruct the source plane to restore a fair balance. In the optical and ultraviolet, Hubble maps the stars themselves. Blue arcs trace young populations. Smoother, redder light sketches older backbones. Fine structure, spiral arms, bars, clumps repeats along the arc, like a motif sampled and remixed by gravity. Because these bands can include compact light from star clusters or quasar cores, they are the most vulnerable to microlensing. Tiny, time-variable flickers superposed on the larger lensing pattern reveal the graininess of the lensing galaxy's stellar foreground. At high energies, X-rays cut to the engine room. Lensed quasars shine in X-rays from their hot coronas, the tiny regions where magnetic fields upscatter light to extreme energies. X-ray microlensing is strong precisely because the emitting region is so small. When one lensed image brightens in X-rays without a matching change in the optical, stars in the lens have briefly magnified the corona alone. Comparing delays and microlensing strengths across bands lets astronomers map the inner architecture of the black hole's immediate neighborhood. Cluster lenses bring one more band into play: microwaves. Hot electrons in a cluster's gas slightly boost the energy of passing microwave photons, carving a spectral dent known as the Sunyaev-Zeldovich effect. That imprint measures pressure, independent of distance. When you lay the SZ map over the lensing mass map, you see whether the gas and the gravity agree. In calm clusters, they track. In violent mergers, they pull apart, revealing shocks, sloshing, and the aftermath of cosmic collisions. Multi-wavelength timing unlocks geometry. If a source varies, each image carries the same rhythm shifted by a delay set by path length and gravitational depth. Catch the beat in multiple colors, and you learn who is doing the delaying: global mass, small clumps, or stars, and you pin down the expansion scale with fewer assumptions. Even steady sources benefit. Spectral energy distributions gathered through a lens reach fainter, earlier galaxies than we could otherwise study, and the lens's magnifying power buys reach. Lensing itself is achromatic, but two color traps lurk. The first is dust. A lensing galaxy can redden one image more than another, mimicking magnification differences. Cross-checking with radio or far infrared, where dust is transparent, exposes the trick. The second is differential magnification again. Different parts of a complex source are boosted by different amounts. If one bright knot dominates a band, the overall color can skew. Careful source plane reconstructions and comparisons across bands bring the true colors back. Polarization adds a quiet, powerful layer. Radial polarization threads reveal magnetic fields in jets and star-forming disks. Lensing preserves surface brightness and, to first order, polarization angles while stretching the canvas. That combination lets astronomers map field geometry on scales otherwise unreachable, testing how turbulence and feedback weave fields through young galaxies and how jets carry ordered magnetism across thousands of light years. Put all the colors together and a pattern emerges. Cold gas outlines, supply lines, dust marks, hidden nurseries, infrared pinpoints young stars, and warm cocoons. Optical light sketches structure. Ultraviolet highlights the freshest clusters. X-rays and radio mark compact engines and shocks. Microwaves weigh the hot atmosphere that binds it all. The lens does not replace any band. It coordinates them, turning a distant, anonymous smudge into a character study with motive and means. There is a human reason this matters. Single images can mislead. One band suggests a calm disk. Another reveals a buried starburst. A third exposes a jet punching a hole through the gas. Only by layering the spectrum do we see cause and effect winds, sculpting dust, inflows feeding cores, shocks lighting X-rays where radio maps show compressed fields. Lensing is the invitation that gets us into the room. Multi-wavelength vision is how we understand the conversation once we are there. Carry this summary forward. Gravity bends every color the same way. Matter emits different colors for different reasons. Lensing sets the stage. The spectrum writes the script. Together, they turn Hubble's impossible arcs into working blueprints of galaxies under construction and black holes at work. In the next section, we'll switch from what lensing shows to how it can fail us and why learning its limits, model degeneracies, line-of-sight clutter, and selection biases keeps our conclusions honest. Limits are not a weakness. They are the guardrails that keep our picture honest. Gravitational lensing looks clean in a poster bold arcs, tidy rings, but every result sits on assumptions, clutter, and noise. Knowing where lensing can fool us is how we keep the impossible images from telling impossible stories. Begin with the models. To turn shapes into mass, we pick a lens family, an oval halo here, a few satellites there, and tune parameters until the predicted arcs match the data. That necessary step hides a classic trap called the mass sheet degeneracy. If you smear a thin, uniform sheet of mass across the whole field, you can rescale sizes and magnifications while leaving many image shapes nearly intact. Different mass maps can yield almost the same picture unless we add outside clues, stellar motions in the lensing galaxy, absolute magnifications from standard candles, or time delays from variable sources. A close cousin is the source position transformation. Nudge the reconstructed source and tweak the lens slope, and the images barely change. Our priors, how we assume mass, should look matter. Parametric models with smooth halos are efficient and interpretable, but they can bias answers if the real halo is boxy, lopsided, or packed with clumps. Free-form, grid-based maps capture odd shapes but can overfit noise. The healthy habit is to compare multiple methods, test them on realistic mock data, and trust conclusions that survive those cross-checks. Now add line-of-sight clutter. The main lens is not alone. Small halos sprinkled between us and the source nudge the light by tiny amounts. Together those nudges show up as external convergence and shear, which shift magnifications and time delays. Ignore them, and you may weigh the lens too high or too low, or infer the wrong cosmic expansion rate. Wide-field imaging and redshift surveys in the same direction let us estimate that extra pull, and modern analyses carry that uncertainty through to the final numbers. Selection bias is quieter but pervasive. We detect what stands out: high contrast arcs near critical curves, neat rings, bright quasar multiples. Those crowd pleasers do not represent every lens or every background galaxy. They prefer certain shapes, environments, and source types. If we forget that, We might overestimate how common massive substructure is, or misjudge the average boost for faint galaxies. The cure is statistics large, well-defined samples, and analyses that model the survey's finder's bias alongside the physics. Differential magnification muddies the view inside a single system. A complex source, a dusty starburst with a buried core, and several bright clumps does not get boosted evenly. Patches landing close to a caustic can dominate one band, skewing colors or inflating an inferred star formation rate. Source plane reconstructions fix this only when the lens model is sound and we have sharp, multi-wavelength data to separate the components. Microlensing adds a lively layer of noise. Stars in the lensing galaxy act as tiny lenses that flicker the brightness of compact regions in the background source. A quasar's X-ray corona, or innermost optical disk, can brighten or dim in one image without a matching change in its siblings. For time delay cosmography, that flicker can blur intrinsic variability and bias delays a bit. Observers blunt it by using light from larger regions, narrow emission lines, radio jets, by monitoring longer, and by explicitly modeling the microlensing alongside the main lens. Dust complicates everything that uses color or flux. If one image passes through a dustier patch of the lensing galaxy, it will look redder and fainter for reasons that have nothing to do with mass. Comparing bands where dust is transparent, fitting extinction curves along each sightline, and leaning on radio or millimeter data where dust is harmless keeps us from blaming gravity for what grains have done. Even perfect physics passes through imperfect instruments. Hubble's point spread function, the characteristic way a point source is blurred by optics and detectors, smears fine structure in every frame. If we misestimate that blur, we can invent or erase tiny kinks in an arc. Subtracting the bright glow of the foreground lens is another delicate step. Small residuals can tilt the brightness balance enough to fake or hide a subhalo. Teams work around this with careful modeling, repeat imaging at different roll angles, and forward modeling that fits lens light and lensed source light together rather than cleaning one and for the best. Kinematics help, but with their own caveat: the mass anisotropy degeneracy. Stellar speeds inside the lensing galaxy depend on both the mass profile and the mix of orbital shapes. Without spatially resolved spectra, a heavier, more tangential model can masquerade as a lighter, more radial one. Two-dimensional velocity maps break that ambiguity and lock down the inner slope of the mass, exactly the information that time delay work and substructure searches need. Redshifts and distances set the geometry. A wrong or fuzzy redshift for the source or any perturbing halo shifts the whole reconstruction. Photometric redshifts are fast, but coarse. Spectroscopic redshifts pin the map down. When sources are faint, getting those spectra is hard work, and the leftover uncertainty must be carried forward honestly. Cluster lenses add crowd control. Every member galaxy contributes a local tug, and the cluster's hot gas adds a smoother pull. Leave out a faint satellite near an arc or misweigh the gas, and the model bends in the wrong spots. That is why the best cluster maps include dozens to hundreds of galaxy halos scaled to their light and are cross-checked against X-ray and microwave maps of gas pressure. Put all these caveats together and a pattern appears. None of them breaks lensing. Each one reminds us to be humble. Robust results are the ones that survive multiple bands, multiple methods, and independent data sets. When an Einstein ring fixes the total mass, stellar motions fix the inner shape. Wide-field imaging constrains the environment, and time delays anchor the distances, and they all agree we can trust the number on the scale. The reward for this discipline is not just accuracy, it is discovery with confidence. Clean maps expose dark subhalos without overclaiming. Honest error bars tell us whether tensions with other measurements are hints of new physics or simply echoes of systematics. And the pictures themselves become even more beautiful because we know what they are and what they are not. Next, we turn from limits to leverage. How clever observing strategies from blind Surveys to targeted follow-ups in machine learning are multiplying the number of lenses and turning rare curiosities into everyday tools. Finding more lenses is a game of scale and pattern recognition. The sky is huge, and strong lenses are rare. Only a small fraction of galaxies sit in the right place and have enough mass to bend background light into arcs or rings. The first rule is simple. Scan enormous areas with uniform, sharp imaging. In those seas of pictures, true lenses stand out like ripples around a submerged rock if you know how to look. Astronomers use three main paths. First, visual hunting. Humans are excellent at spotting odd geometry, so teams review big image catalogs by eye, often with citizen scientists. Give volunteers a clear rule. Click if you see a blue arc around a red galaxy, and a mountain of data becomes a short list fast. Experts then vet the list. It is old school, but it works, and it teaches what lensing really does to a scene. Second, spectroscopic selection. A single fiber can light from a foreground galaxy and, by chance, from a background galaxy behind it. In the spectrum, you see two sets of fingerprints at two different redshifts, one near, one far. That double redshift is a strong clue the pair is aligned. High-resolution images of those suspects often reveal the arcs the spectrum hinted were there all along. Third, automation. Modern classifiers learn from examples. Feed a neural network millions of labeled cutouts, lens, and not a lens, plus tricky look, a like face, on spirals, tidal tails, and it learns the subtle curves, color contrasts, and context that give a true arc away. The best systems do more than thumbs up or thumbs down. They rank candidates and highlight the pixels that drove the call so a human can audit the decision. Feedback loops then improve the model after every confirmed hit or miss. Time adds another axis. Some of the most valuable lenses are not static. Lensed quasars that flicker and lensed supernovae that pop and fade. Time, domain surveys watch the same fields night after night. Software looks for pairs or quartets of points that vary together with slight delays. When the rhythm matches across multiple images, the system raises a flag. Follow-up telescopes jump in to measure delays and redshifts, turning a maybe a clean cosmography tool. Once a candidate is on the list, confirmation is a choreography. Space telescopes or ground telescopes with adaptive optics take sharp images to resolve arcs only an arc-second wide. Integral field spectrographs slice the scene into thousands of tiny spectra, letting us map velocity and chemistry across the stretched source, while separating it cleanly from the lens galaxy. Radio and millimeter arrays check whether the structures appear where dust is transparent. Each instrument adds a layer until the candidate is confirmed or rejected with confidence. False positives are common. Star-forming rings inside a nearby galaxy can mimic an Einstein ring at first glance. Spiral arms can curl into arc-like shapes, and mergers can throw out long tidal tails that trick people and software. That is why color, context, and redshift matter. A true lens almost always pairs a red, massive foreground galaxy with blue, higher redshift features wrapped around it. Spectra that show two distances seal the deal. Speed matters, too. For lens transients, predicting where the next image will appear and when it will arrive lets us point the right instrument at the right place at the right moment. A typical sequence goes like this. Detect a faint first image. Model the lens quickly, forecast the reappearance, then set a spectrograph on the predicted spot to catch the next image in. When the sky keeps the appointment, the payoff is huge clean time delays, rich spectra, and a direct test of the model. Behind the scenes, alert brokers knit the pipeline together. They ingest nightly alerts from wide surveys, cross-match them against catalogs of known massive galaxies and clusters, and score each alert for lens likeness. High scorers trigger automatic requests for deeper imaging or spectra. The system learns from its history. Every false alarm and every confirmed lens updates the training set, so the next pass is sharper. This flood of lenses changes the science. With dozens, then hundreds, then thousands of systems, we can separate trends from flukes. We can measure how common subhalos are without leaning on one showpiece. We can how halo shapes depend on environment. We can build clean samples of lensed galaxies at fixed cosmic times and compare their sizes, rotations, and star formation rates fairly. Statistics turn pretty pictures into population studies. Still matter at every stage. Citizen scientists catch oddballs that confuse algorithms, invent new tricks to break degeneracies. Instrument teams push sharper images and steadier spectra. The culture has shifted from a few famous lenses to an ecosystem where discovery, vetting, modeling, and follow-up run continuously and feed each other. If you want a mental picture, imagine a production line that turns starlight into knowledge. Raw images go in. Candidates roll onto a belt. Robots stamp likely or unlikely. Human inspectors pull the best onto a separate track. Precision tools shape the raw piece into a finished product, a mass map, a time delay, a reconstructed baby galaxy. The factory never sleeps, and every finished part snaps into a larger machine, our model of how gravity and structure evolve across time. All of this leads to a future you can feel coming. The more lenses we find, the sharper our questions become. How small can a dark matter clump be and still survive? How early did disks settle and start to spin? How much do massive halos twist space, and does that twist change with time? Finding lenses faster is not a race for records. It is how we turn an impossible image into a routine measurement, and a routine measurement into a new test of physics. Next, we look ahead to the observatories that will supercharge this hunt wide, deep, and fast, and how their partnership with Hubble-class imaging will make the rare become common and the faint become clear. Think about what happens when you marry gravity's optics to the newest sky machines. Wide, deep, and fast surveys trawl the heavens for the rare geometry of a strong lens. Sharp, space-based imagers and multi-giants then swoop in to interrogate each find. The result is not one or two, but an assembly line of measurements, time delays, maps, and source reconstructions done at scale. Begin with the widest net, a decade-long movie of the southern sky that watches billions of galaxies night after night. Its cadence turns lensing into time, domain astronomy, pairs and quartets of points that brighten the same rhythm with small delays get flagged automatically. Arcs that flex as a supernova rises and fades are caught in progress, not the fact. Forecasts for next image arrival can be issued in real time, letting follow-up teams plan spectroscopy before the rerun appears. A wide infrared cartographer adds complementary power, uniform, stable, space, quality imaging, and spectroscopy over an enormous footprint. Its sweet spot in wavelength pierces dust and cleanly separates red, distant sources from nearer, redder lenses. Even without dramatic arcs, a gentle, coherent stretch across millions of background galaxies sketches the invisible scaffolding of dark matter on cosmic. Strong lenses within that map come pre-contextualized. Each sits atop a well-measured environment. Now at a telescope that takes Hubble's crispness and scales up the field of view dramatically. Instead of framing one or two lenses at it can tile the sky with Hubble-class in the infrared, capturing fine caustic structure, faint central images, and tiny wiggles that betray dark subhalos, all in survey mode. For time delay cosmography, its stability and low noise mean bright, clean light curves without atmospheric hiccups, and integral field spectrographs can read stellar motions in the lensing galaxy to break mass anisotropy degeneracy. None of this replaces the microscope we already have that sees the reddest light with exquisite detail. When a wide survey raises a flag, supernova due to reappear here in 3, those infrared eyes dissect the rerun, prying open the chemistry of the blast and the structure of the host while the geometry clocks in the background. For lensed galaxies, the same instrument's spectral resolution separates the dance of gas and stars across each reconstructed spiral arm, letting us test whether a system is a settled disk or a messy merger. Cold gas dust demand different ears. At millimeter wavelengths, a premier interferometer turns boosted, dusty starbursts into high-fidelity flow charts, rotating rings, infalling streams, and wind-blown cavities mapped in molecular lines. Because those emissions come from extended regions, they sidestep microlensing and pin down the smooth part of the mass model. In parallel, new radio arrays with sprawling baselines, time-variable, lensed quasars with high precision, cross-correlating light curves to extract delays even when weather interrupts. High energies finish the portrait. X-ray observatories isolate the tiniest, hottest regions around black holes. In a lensed quasar, one image can flare in X-rays alone as a single foreground star acts like a microtelescope on the corona. That differential microlensing across bands, X-rays versus optical versus radio, tells us the true size of the accretion zones and gives independent leverage on the graininess of the lensing galaxy's stellar sea. Fold those constraints back into the lens model, and both the mass map and the source reconstruction tighten. Crucially, these observatories are being wired to talk to each other. Public alert streams publish every transient. Brokers cross-match those alerts with catalogs of massive galaxies and clusters. Machine learning filters rank the lens likelihood and push the best to follow-up cues. A detection one night can trigger space-based imaging, radio timing, and infrared spectroscopy within days. For forecastable reappearances, teams schedule deep integrations at the predicted minute, turning the sky itself into a scheduled laboratory. This orchestration changes what questions we can ask. With tens of thousands of clean lenses, we can measure how often small dark matter clumps occur and how their abundance shifts with environment. With hundreds of well-timed lens supernovae and quasars, we cross-check the expansion rate using geometry and timing alone. With uniform, sharp reconstructions of early galaxies, we can map how rotation, turbulence, and metal enrichment grow from one cosmic epoch to the next, anchored to the same selection and modeling. It also changes how we control error. Wide surveys provide the environment line-of-sight structure, galaxy counts, and shear fields, so external convergence and selection effects are measured, not assumed. Space-quality imaging fixes the inner mass slope, while spectroscopy locks down stellar kinematics. Radio and millimeter data suppress dust and microlensing biases. X-rays probe the tiniest scales. When all of these agree on the same mass, the same delays, and the same subhalo bumps, systematics have fewer places to hide. There is a human texture to this future. Citizen scientists will still spot the weirdos that algorithms miss. Rapid response teams will keep night watch for predicted echoes. Modelers will iterate live, refining mass maps as new light curves and spectra arrive. The cadence of discovery will feel less like single papers about single objects and more like weather reports. Today's new lenses, this week's confirmed delays, next month's forecasted reappearance. Strip away the acronyms and hardware, and the promise is simple. We are building a partnership where one machine finds, another confirms, another dissects, and all of them learn from each other in real time. Gravity provides the optics, telescopes provide the eyes, software provides reflexes. Together, they will turn Hubble's impossible images into a daily language with we weigh the dark, time the expansion, and read the blueprints of galaxies being born. Next, we'll zoom back to Hubble's original puzzle pieces, the famous rings and arcs, and tell the origin stories behind a few of them, what they taught us the first time we saw them, and what they still whisper now that our tools have grown sharper. Let's put faces to the physics. The illusions feel less like magic when you know the stories behind a few famous frames. First, the twin that proved the idea. A bright quasar in the distant universe appears twice in the same small patch of sky. Two star-like points, separated by a sliver of dark. They are not sisters. They are one object seen along two bent paths past a massive foreground galaxy. The clincher is timing. When the quasar brightens in the true sky, one on our detector echoes the change first, and the other follows after a built-in delay. That lag is gravity's signature. It announced that the sky itself contains lenses and that we could use their delays to measure distance and, eventually, the expansion rate. Hubble's sharp vision locked down the positions and host galaxy glow around each image, the details you need to turn a pretty picture into a number. Next, the 4-point cross that looks like a logo. Aim at a nearby, face-on spiral galaxy. At its center, you see 4 equally spaced points wrapped around the core like a jeweled pin. That is a single quasar into 4 images by the galaxy's central mass. The drama here is small-scale structure. Each point twinkles differently over time. Stars in the lensing galaxy act as tiny lenses of their own, briefly boosting one image while leaving the others alone. That flicker microlensing lets astronomers probe both sides of the scene once. The graininess of the lensing galaxy's stellar field and the size of the quasar's innermost light-making regions. The cross is proof that lensing is layered. The big halo makes the fourfold split. The stars add the shimmer. Now zoom out to a whole cluster and its dragon-shaped arc. In a golden swarm of galaxies, a single electric blue ribbon curves around the center, broken into knots that like a refrain. This was one of the first strong lensing arcs to grab attention. A background galaxy stretched and brightened by the clusters into a visible line. Hubble deepened the view, revealing that the ribbon is a stitched set of mirror, flipped copies of the same galaxy. Model the lens, map those repeated knots back to their original places, and a baby galaxy steps into focus with far more detail than would otherwise be possible. The same reconstruction gives you a mass map of the cluster, including the dark matter that does not glow. In one go, you get a portrait of a young galaxy and a weigh-in of an entire city of galaxies. Some pictures change the dark matter debate. In a pair of merging clusters, glowing X-ray gas, most of the visible mass has been shocked and lags behind. But when you use lensing to map gravity, the mass peaks sit with the galaxies that sailed through, not with the slowed gas. Light says one thing, gravity says another. That separation is hard to explain with clever gravity alone. It makes sense if most of the mass is in a weakly interacting, invisible form that passes through the collision like a ghost. The image is quiet and clinical, but it carries weight. It is a clean case that the universe's main ingredient is dark and does not stick to itself the way gas does. Then there is the supernova that came back on cue. In a crowded cluster field, Hubble watched a single star explode behind a lens. One path delivered the first image, and months later, other paths reruns in different parts of the frame. Modelers used the early images to forecast when and where the next appearance would land. The sky kept the appointment. That success did 3 things at once. It validated the lens model, turned the delays into a measure of cosmic distance, and gave astronomers a chance to perfect spectra at the exact moments they wanted. A dying star became a stopwatch and a test of map. Perfect circles tell their own story. In a handful of systems, alignment is so tight that a background galaxy draws a nearly ring around its lens. At first glance look like special effects shots. In truth, they are workhorses. The ring's radius is the Einstein radius, a built-in ruler set by the lens mass and the geometry of distances precisely, and you weigh the lens without counting a single star. Zoom in, and the ring is not uniform. It has bright beads and dim gaps. Those tiny bumps are clues to small-scale clumps in the lens satellite galaxies you can just barely see, and subhalos with no stars at all. Perfection, when inspected, becomes a laboratory for imperfection. Each of these scenes taught a different lesson. The twin quasar taught timing. The 4-point cross taught microlensing and the size of quasar engines. The dragon arc taught reconstruction and dark matter mapping. The colliding clusters taught that gravity follows an invisible component that not slow down with gas. The scheduled supernova taught and calibration. The clean rings taught weighing and substructure. Together, they say that Hubble's impossible images are not a gallery. They are a toolbox. A pattern emerges when you read them side by side. The foreground, whether a single galaxy or a rich cluster, sets the stage with its mass. The background source supplies texture knots, disks, jets, explosions that can be split, stretched, or delayed. The space between contributes line-of-sight nudges. You must count fairly, and your detector, with its own blur and noise, must be modeled alongside the sky. When all of those layers are respected, the illusions line up with the math, and the pictures turn into measurements you can trust. There is also a human arc that runs through these cases. Early finds were one-offs, celebrated for their strangeness. As techniques sharpened and samples grew, the same kinds of objects became tools. What looked rare became routine. What looked like a trick became a ruler, a clock, and a microscope. That shift from "look at that" to "measure with this" is the quiet revolution behind every headline image. Keep these stories close as we turn to a quieter question that shapes how the public sees all of this. Why do Hubble's arcs look blue and the foreground clusters look golden? How are the colors chosen? What is true color in space? And how do image makers keep beauty from bending the truth? The answers matter because the way we paint the sky affects what people think the sky is saying. Color in a Hubble image is not makeup, it is a translation. Hubble's cameras do not snap color photos the way a phone does. They record several monochrome exposures through filters that pass slices of spectrum. Image makers then assign those slices to red, green, and blue and combine them. Done carefully, the result is both beautiful and faithful to the physics. So why do the foreground cluster galaxies warm and golden while the lensed arcs look icy blue? 2 reasons. First, cluster members are mostly old, red stellar populations with little fresh star formation, so their light peaks at longer wavelengths. Map filters in the usual chromatic order: bluest filter to blue, mid to green, red to red, and they glow amber. Second, many background sources are actively forming stars that shine strongly in the ultraviolet. Redshift slides that UV into optical blue for us. But true color in space is slippery. Human eyes evolved for sunlight, not galaxies at cosmic distances. Galaxy 10 billion light-years is dim, and its light has been stretched redward by expansion. If you stood beside it, you can't. You would see almost nothing. The goal is not to reproduce an eye view no human could have. It is to encode the spectrum honestly. 3 simple rules help. Keep the ordering of colors sensible. Keep relative brightness meaningful, and be transparent about choices. There are 2 main approaches. Natural color composites use broad filters that correspond to red, green, and blue light. When possible, these look close to what an extremely sensitive eye might perceive nearby. Representative color composites use narrow or medium filters, often tied to specific emission lines like hydrogen alpha, oxygen O3, or sulfur S2, and map them into RGB in a chosen order. The famous Hubble palette for nebulae assigns S2 to red, H alpha to green, and O3 to blue. It is not fake. It is a consistent of physics. Lensed fields usually mix both styles. Broad filters set the general hues of stars and arcs. Selected narrow bands isolate features like ionized oxygen in a distant galaxy or shock fronts near a jet. Because lensing is achromatic, gravity bends every wavelength the same way. The same arcs appear in all bands, but each band highlights a different layer of the story. Stretching is the other quiet decision. Raw frames span a huge dynamic range. Bright cluster cores and dim arcs share the same scene. A simple linear stretch would blow out the cores or bury the arcs. So processors use nonlinear stretches, arcsin, logarithmic, etc., to lift the faint without clipping the bright. Done well, this preserves structure across the whole field. Done poorly, it can invent halos or turn noise into wisps. The guardrail is to document the stretch and avoid painting in details that aren't there. Sharpening has similar risks. Every telescope blurs a point into a small pattern, the PSF. Software can partly undo that blur, deconvolution, and improve local contrast. Push too far, and you get ringing, fake ripples around stars, edges on smooth arcs. For lensing, where tiny wiggles can imply dark subhalos, restraint matters. Many teams model the lens and source in the native, blurred space and present deconvolved images as illustrations, not as measurement inputs. Color balance is a choice with consequences. Push blue too hard, and background arcs shout while faint red galaxies, the quiet majority fade. Warm the frame, and old cluster light looks great, but young knots hide. A common practice is to anchor star colors with objects of known spectra, set a neutral white for a G-type star, and let the rest follow. Some releases showed two versions, a natural composite and a science composite that emphasizes a particular emission line or structure. Dust can mimic color. If one sightline through the lensing galaxy is dustier, that image of the background source will look redder and fainter for reasons unrelated to mass. Cross-checks at longer wavelengths, infrared, radio, millimeter, where dust is transparent, reveal whether you are seeing physics or a dirty window. In the script of a lensed field, dust is the stage fog you must account for in every scene. Behind the scenes, alignment and combination are meticulous. Multiple dithered exposures are drizzled together to recover resolution and reject cosmic rays. Foreground light from the lensing galaxy is modeled and subtracted, so arcs are not drowned in glare. Subtraction must be gentle. Too aggressive, and you carve away real features. Too timid, and you bias brightness ratios that later test for dark substructure. The ethic is simple: show, don't sculpt. Color should guide attention to physics that is truly old versus young stars, dust lanes, emission, line regions, without inventing drama. Good captions name the filters and mappings. When teams do this, beauty becomes a doorway to understanding instead of a distraction. Keep one more nuance in mind: differential magnification. A complex source rarely gets boosted evenly. If a star-forming knot lies near a caustic, it can be amplified far more than the rest and dominate one band. That skew can make a galaxy look bluer or redder than it is. Reconstructing the source plane with a solid lens model restores a fair color balance. For your ears, the human summary: Hubble does not paint the sky, it translates it. Old cluster galaxies wear gold, their stars are elderly. Lens darks glow blue because they are young and far, their ultraviolet shifted into optical bands. Narrow filters can make specific gases sing. Non-linear stretches lift faint structures into view. None of this is deceit. It is grammar for light stretched thin by distance and time. Hold this color literacy as we return to the illusions. Next, we'll turn it into a pocket field: how to spot the fast-looking jet that is not breaking light's limit, how to name an Einstein ring on sight, and how to explain both in one sentence to anyone who asks. Pocket field time. If you're staring at a Hubble impossible scene and a friend asks what they're seeing, here's a quick, human way to decode it: fast, clear, and true. First, how to spot an Einstein ring or arc. Look for a bright, heavy-looking galaxy or a golden cluster near the center. Now check the blue features around it. Do they curve in smooth, circular arcs that share a common center? That's the tell. Gravity bends light tangentially, so real lens arcs wrap around the lens like paint on a hoop. A perfect lineup can draw a near circle. A slight miss breaks the circle into one or two long arcs. If you notice the same little blue knot repeated along an arc, you're seeing one background galaxy echoed by the lens. Second, how to avoid lookalikes. Spiral arms and star-forming rings can fool you. Ask, what are these blue curves wrapping around? If they wrap around their own galaxy's center, you're probably looking at a nearby spiral, not lensing. In lensing, The arcs wrap around a different, often redder, foreground galaxy. Another clue, tidal tails from mergers fling outward in messy, one-sided streams. Lens arcs are balanced and center-seeking. If you could take spectra, a true lens shows two distances, one near, one far. Third, the faster-than-light jet illusion. You might see a straight, narrow beam from a galaxy's core, with bright knots that seem to leap ahead too quickly. Ask one question: is one side much brighter than the other? If yes, you're seeing relativistic beaming radiation squashed forward along the jet that points almost at us. The knots are racing at just under light speed, and perspective compresses their timing so their apparent motion looks superluminal. The counterjet is usually dim or invisible because beaming points its light away. How to read time delays by eye. When a variable source is, say, a quasar that flickers, you get 2 or 4 look-alike points near a foreground galaxy. Watch long enough, and you'll notice the same up and down brightness pattern in each, staggered in time. It's like a stadium wave that hits one section, then another. That stagger is the delay caused by different path lengths and different dips through the lens's gravity well. Rhythm. Offset beats. That's a lensed variable. Fifth, where dark substructure hides. Rings and long arcs should have fairly smooth brightness if the lensing mass is smooth. If one segment is oddly bright, or a small kink shifts part of the arc without moving its ends, a hidden clump is adding a local tug. A steady, wavelength-agnostic anomaly points to a dark subhalo. A fickle, color-dependent twinkle is usually microlensing by stars. Radio and millimeter images are lie detectors here. They're mostly immune to microlensing and preserve true brightness patterns. Sixth, what color is telling you? Warm gold usually means older stars in the foreground lens or cluster. Icy blue often means young star formation in the distant, lensed galaxy, shifted into our optical bands by cosmic expansion. If a release used narrow filters, neon greens or electric blues can mark specific gases, like oxygen or hydrogen. Remember, the color map is a translation of the spectrum, not paint. Good teams list which filters went to which colors. Seventh, a one-sentence explanation you can give to anyone. You're seeing the same distant galaxy along several bent paths around a heavy foreground mass. Gravity acts like a lens, stretching and copying the image, and sometimes delaying it. While fast jets can look faster than light because of perspective, but nothing actually breaks physics. Now a handful of pocket cues worth memorizing. Roundness check. Draw an imaginary circle centered on the lens galaxy. Do the blue features that circle? If yes, lensing. If not, suspect spirals or tidal debris. Tangential radial. Real lens arcs are stretched tangentially around the center, not radially, like spokes. Spoke-like features usually belong to a nearby galaxy's internal structure. Mirror twins. If two blue patches on opposite sides look like flipped versions of each other, that's classic lens symmetry. Odd image whisper. Smooth lenses make an odd number of images. One tiny, demagnified image hides near the lens center under the galaxy's glare. Delay. Deepest path, longest wait. Light that dives nearer the center arrives last. Energy, honesty. Lenses conserve surface brightness. Magnification makes things bigger, not intrinsically brighter per square inch. The lens adds energy. It stretched the canvas. Dust trap. Image redder than its siblings? Before blaming mass, check for dust in the lensing galaxy's disk along that sightline. Jet parity. Bright jet toward us, faint counterjet away. If you can barely see the far side, beaming, not new physics, is doing the talking. Why this field guide matters is simple. Most of the time, you won't have a caption or a spectrum on tap. You'll have a striking frame and a few seconds to decide whether it's a portal, a trick, or a measurement. With these cues, you can enjoy the beauty and still keep your feet on solid physics. You'll know why a ring is a ruler, why a flicker is a clock, and why a too fast jet is a mirror, not a mutiny, against relativity. Carry these tells into every deep sky image you see. They turn awe into understanding without stealing the awe. And once you learn to spot the patterns, you'll notice them everywhere because gravity's handwriting is consistent, and Hubble has been teaching us how to read it for decades. Let's stitch the ideas together and ask what they mean for all of us, not only for astronomers. Hubble's impossible images are training wheels for thinking in space-time. They teach 3 habits. First, do not trust straight lines when the stage is curved. Second, do not trust clocks when motion and perspective compress time. Third, when a picture feels like a magic trick, look for the simple rule that makes the trick repeatable. Those habits turn awe into understanding without draining the awe. Start with curvature. In daily life, we assume the shortest path is straight, and that light travels straight. Asks us to upgrade that instinct. Mass curves space. Curved space offers more than one straightest route, and light samples those routes. Bring that back to Earth, and it helps more than you think. Navigation satellites already correct for relativity. They're clocks differently in orbit than on the ground. Engineers account for that, or you would drift. The sky is a classroom, and lensing is its chalkboard. Next, perspective. The fastest-looking jet in a Hubble frame is not breaking light's limit. It is using angles and timing against our intuition. That same caution applies to videos and everyday graphs. If a trend looks impossibly steep, check whether the axis was squeezed or the sampling was uneven. If a car in a side mirror jumps, it is not teleporting. It is slicing across a compressed view. Superluminal jets are the cosmic version of a familiar trap. Speed inferred from snapshots that hide geometry and timing. Third, repeatable tricks. Lensing patterns obey rules. Arcs stretch tangentially. Multiple images arrive in a specific order set by path length and gravitational depth. A perfect lineup draws a ring. A near miss draws arcs and twins. Once you know these tells, you can spot lenses by eye and explain them in one sentence. When an idea can be taught simply and checked against the next image, it graduates from curiosity to tool. Tools change what we dare to ask. Because we can weigh dark matter with lensing, we can ask how grainy it is and whether it clumps the way cold dark matter predicts. Because we can turn delays into distances, we can ask whether the expansion rate inferred from the early universe agrees with the rate measured nearby. Because we can reconstruct baby galaxies, we can ask how fast disks settle, how quickly metals spread, and how feedback sculpts gas. Questions sharpen models. Models tell us what to look for next. The loop tightens. There is also a lesson in humility. Every strong lensing field has clutter we cannot see. Stars that flicker brightness, small along the line of sight, dust that reddens one path more than another. The honest response is not to shrug. It is to add data and cross-checks. Use radio where dust is harmless. Use X-rays where compact regions glow. Use stellar motions to fix the inner mass slope and wide-field imaging to weigh the environment. When independent layers converge on the same mass, the same delays, the same substructure, confidence rises. People and machines share that work. Citizen scientists still spot oddballs. Algorithms scan millions of cutouts without blinking. Modelers build mass maps that compute in seconds what once took weeks. None replaces the others. A person notices a pattern the network did learn. A network flags a faint symmetry a person would scroll past. A modeler encodes a physical prior that keeps both from chasing noise. The result is less romance and more reproducibility, a good trade when you want numbers that survive peer review. A single Hubble frame can feel like a poster, full of color and drama, but light on plot. Once you read it, the plot is crisp. Foreground, the lens, red and old. Background, the source, blue and busy between them. A curved stage with multiple light paths and built-in delays. That is why we talked about color choices, point spread functions, caustics, and critical curves. Knowing the grammar lets you separate art from artifact and turn pictures into measurements. About that word, illusion, nothing here is fake. The ring is not a portal, it is a ruler. The echo is not a rewind, it is a delay. The jet is not breaking a law, it is leaning into perspective. Illusion, in this story, means the universe is speaking a language our instincts did not grow up with. We learn the language, and the illusion dissolves into a lesson. Where does Hubble fit now that new observatories share the sky? It remains the storyteller with a steady hand. Its long baseline of sharp, stable imaging, time delay work, subhalo searches, and reconstructions. New machines widen, deepen, and quicken the hunt, but turning a candidate into a calibrated measurement still leans on careful, space-quality eyes. The partnership is a relay. Wide surveys find, space imagers confirm, radio and millimeter arrays map cold gas, X-rays probe the engine room, and timing stitches it together. Think of the closing loop like this. A wide survey flags a likely lens. A team confirms an Einstein ring and measures its radius. Stellar kinematics fix the inner slope. Radio maps rule out micro-lensing. A lensed supernova in the same field adds delays that lock down distances. The mass map that emerges weighs the lens, counts its clumps, and reveals a magnified baby galaxy with spinning gas and patchy metals. All from one impossible picture, read with the right grammar. Hold that loop as we step into the final chapter. We will tie the pieces together, the ring, the echo, the jet, and the mass, and close where we began, with a frame that looks wrong until you know how to see it right, and a universe that feels larger, not smaller, once the trick is explained. A single frame can carry a lifetime of lessons, so return to the picture that started this journey. A heavy, golden cluster at center, cool blue arcs wrapped around it like spilled paint, a slim jet that seems to sprint beyond reason. At first glance, the scene looks like a collage. It is one event told along many paths. Mass has curved space. Light has obeyed the curve. Motion and perspective have bent a sense of time. That is all, and that is enough to remake how we see. The ring is the simplest place to plant your feet. It is not a portal. It is a ruler drawn by gravity. Line up a galaxy, a massive lens, and a telescope, and space-time offers multiple straightest routes the same light. Where those routes focus, a circle appears at the Einstein radius. Measure it, and you weigh the lens. Watch it in multiple colors, and you separate old stars from newborn clusters, dust from clean lanes, and quiet from gas lit by shock and wind. Treat it as more than a picture, and it becomes a scale, a clock, and a microscope at once. The echoes come next. A quasar flickers, a supernova rises and fades, and the lens splits that rhythm across the sky. Each image carries the same beat, shifted by a delay that encodes path length and gravitational depth. Record those delays, and the geometry turns into distance. With enough clean echoes, the expansion of the universe becomes a timed walk rather than a ladder of assumptions. Nothing mystical. Deepest dive, longest wait, widest swing, quicker return. The map of mass sets the order. The sky keeps the appointments. That is the guardrail that keeps us honest. Nothing outruns light. Some patterns just look as if they do. A beam of near light speed knots aimed almost toward us squeezes arrival times between snapshots. Add relativistic beaming, and the near side glows while the far side fades. If you ignore the angle, you will compute an impossible speed. When you measure the angle, track the apparent drift, and in the redshift, the numbers fall back under the limit. The lesson travels well. Lines can be a choice of axes, not a scandal in the data. Under the smooth beauty live the bumps that tell us what most of the universe is made of. A perfect model predicts not just where arcs should be, but how bright each segment should look. When one patch refuses to too bright here, too dim there, and the anomaly is steady across time and wavelength, a dark subhalo has tugged the count. Such anomalies across many rings and you count the pebbles in an invisible riverbed. The tally so far favors a cold, clumpy sea of dark matter, many small companions nested inside larger halos. Just as simple simulations said, color is a translation, not a costume. Broad filters mapped to red, green, and blue give you the broad strokes. Narrow filters spotlight particular gases. Non-linear stretches lift faint structure without letting the bright drown it. Good practice tells you which filters went where and keeps deconvolution gentle so math does not masquerade as detail. The goal is not to paint drama, but to reveal it. When the grammar is honest, a blue arc is young starlight shifted into our bands. A golden lens is an older population at rest, and a neon knot is gas shocked into glow. Limits make the science stronger. A mass sheet smeared across the field can mimic magnification. Line of sight halos can nudge delays. Dust can redden one image and fool the eye. We break those ties with outside witnesses. Stellar motions inside the lens fix the inner slope. Radio and millimeter maps ignore dust and microlensing and check true brightness patterns. X-rays isolate the tiniest regions near black holes. Wide imaging weighs the environment. When these layers agree on the same mass and the same delays, systematics have fewer places to hide. Scale changes the wide. Fast surveys turn rare alignments into daily weather. Software flags lens-like geometry and time-shifted rhythms. Citizen scientists still catch the oddballs. Space-quality imaging resolves the arcs, measures the radius, and reveals faint central images. Interferometers map cold gas through the stretch, showing inflows, outflows, and rotation in galaxies we could not otherwise resolve. X-rays and radio time, the compact engines. The pipeline has become up. One machine finds, another confirms, a third dissects, and all of them learn together. Why should anyone outside astronomy care? Because the habits this picture teaches are portable. Upgrade your instinct for straight lines when the stage curves. Respect the clock when motion and angle can compress time. Ask rules before you trust a thrill. Do that, and you carry the best parts of science into everyday life. You'll keep the awe. The ring is still beautiful after you measure it. The echo is still moving after you time it. The jet is still fierce after you explain it. There is a quiet human thread running through all of this. For us, general relativity has felt like a theory extremes. Black holes, big bangs, conditions far from home. Hubble's impossible images pull it into our senses. You can see the curve in a photograph. You can watch a delay arrive. You can feel your first guess fall and a better guess rise. That is not an abstract equation. That is a conversation. The universe speaks. We learn its grammar. We speak back with predictions the sky can keep or break. So far, it keeps them. Hold one last image in your mind. A ring hangs in darkness. It is bright, but not brighter per square inch than the source. It is larger, stretched by a lens that added no light of its own. Elsewhere in the same frame, a pair of points rises in the same rhythm, slightly out of sync. Farther off, a thin beam carries that seem to leap until measurement tames the leap. It all feels impossible until then it feels inevitable. That is the heart of the illusion and the gift of seeing through it. Space is not a rigid stage. Time is not a universal clock. Light is a faithful messenger that will take any path the stage offers. When you learn to read those paths, a pretty picture becomes a working tool and a wonder becomes a way to know. The frame doesn't get smaller when you understand it. It gets deeper, and you have seen a straight story told along a curved path. You start to look for curves everywhere, and you are better for it.